The next presentation, I am sure, will be equally interesting because it is the first one on the evolution of GloFAS. And this will be given by Erwin Joter from the European Center of Medium Range Weather Forecast. And Erwin will present on the upgraded seasonal and sub-seasonal products. And I ask Erwin already to please make sure he stays on time. Erwin, the floor is yours.
Hi, everybody. I was just panicking a little bit because the slider didn't work. So I'm not sure that it's working. Wonderful. Thank you. So hi, everybody. I'm Erwin Joter. I work in the hydrological team at ECMWF, and I'm going to talk a little bit about the revised seasonal and the new sub-seasonal products in GloFAS. So why did we do this? I mean, GloFAS was the first global seasonal hydrological prediction system that was introduced in 2017. I mean, it's quite outdated if you like. And we also had EFAS, which has had sub-seasonal and seasonal components, but lots of similarities with lots of dissimilarities. So we really wanted to have a new system which is modernized and basically homogenized between sub-seasonal, seasonal, EFAS, and GloFAS. So this is what we did. Now we have a set of scripts, set of methods, and products implemented or being implemented for all these. What did we do? We went with kind of like looking out all the products, not all, but a lot of products by other centers and meteorology, hydrology, and chose to follow the calendar weeks for the sub-seasonal with daily updates and the meteorology and the source coming from ECMWF, and in seasonal monthly out to 7 months with a monthly update. And we also made this climatology is common. So now we use the same range-dependent climatologies, which use and are generated from the reforecast 20-year. So hopefully they really provide a consistent setup. We went with 7 categories. So basically the anomalies are expressed in 7 categories, the same as in the European State of the Climate, as you see there. And we also add a simplified representation of the uncertainties. Low, medium, and high uncertainty, well, because we use ensembles, so obviously you want to represent that. And everything is based on the 100 bin climatology that uses the percentiles. We have 2 products, basically the same basis as we have now in the old GloFAS seasonal. We have an outlook which shows the rivers, the pixels colored according to the underlying anomalies and uncertainties, and you have points where you can click and you have further information. And also a basin summary, which aggregates the information onto the basins. Something that's brand new is that instead of providing just one map, which is the worst happening anytime in the 30-day or any kind of like lead time, you can navigate through your lead times and check each individual lead times. But how do we generate? I mean, I'll be quick. We have quite extensive documentation that you can go in, and then if you are interested, you go through all the details. But we have the model climatology. This is basically a collection of values which come from past forecast, these reforecast, and we use them to represent what basically our real-time model is likely to produce, so to say, and whether it's anomalous or not, we will actually use this climatology to define that. So we divided this distribution into 100 equally likely bins by the percentiles. So the first percentile, which represents everything that happens by 1% likelihood in that 20-year climatological period for this season, for this day of the year, or this week, or this month of the year. And that will be the first bin. And then between the first and the second, that's the second bin, and so on and so on and so on, up to the last one, which will be the river discharge values, the mean weekly or mean monthly river discharge values above the 99th percentile. So everything there will be only happening 1% of the time based on this 20-year model climatology. So this is all nice and well, but then we have the forecast. So we have 51 ensemble members. For now, we use ECMWF ensemble forecast. And we want to tell how anomalous, how extreme these values are. So basically, we just find where each of these fall into our 100 bins. The lowest one will be number 54. We internally in the documentation call it as a rank because it's between 53rd and 54th percentile. And the next one is rank 60, and so on up to the largest value, which is the highest in the ensemble, will be getting rank 97. So then it's 51 wonderful anomaly or rank values, but I mean, it's basically too many, so we really need to simplify it. So we went with the 7 main categories. The first one is the extreme low, which is below the 10th percentile. So everything that's the lowest 10% of all the events basically in the climatology. And then from the 10th to the 25th, which is the low category, and then it's a funny name, bit low, and then normal from the 40th to the 60th, bit high, high, and finally extreme high above the 90th percentile. It's only 7, but because we have 3 uncertainty for each of these as a subcategory. So if we want to represent it on a map, then we need to find colors and we need to display it somehow. So to basically make it possible, we merged for the map products, at least the middle 3 into a bigger so-called near normal category. And this way we concentrate on the higher and the lower, the larger anomalies. So the next step, we have the 51 members and we need to say which category has how many members and what is the probability for each of these categories. Obviously, it's counted, the number of members. We have a distribution of these numbers, zeros for the low ones, and then up the highest is the extreme high with 18, which is about 35 probabilities. So this is very simple. And we can also compare this probability distribution, if you want to, with the climatological probability. So basically the size of these categories. But this is really not yet the end of the story, because even 7 probability values are a little bit too many to basically display them on a map or European or global map. So we needed to simplify it even further. And what not to do is that just compute the mean. So we have all these rank values, which gives an anomaly or extremity level for each ensemble members, and we compute the mean. So in this example, from 54 to 97, this averages to around 83, which fall in right in the middle, as you visually also can see, in the middle of the high category. Why not to choose the most likely category? Because that maybe would be the first one people would vote for. The reason we did go with the mean is to avoid jumpiness. And as you go longer and longer lead times, it's more and more likely that you will have higher and higher uncertainty. So your distribution will be pretty even at the long ranges. And in that case, little differences, as in this example, it demonstrates, you can end up with very different, like in this case, low and high anomalies. And the underlying distributions are basically almost the same. So the mean really will guarantee you kind of extracting this kind of expected quantity there. So next step is the uncertainty. Again, naturally, how spread out these rank values are. We use the standard deviation. It's pretty common, and defined a 3-tier system going with 10 and 20 to define kind of like the boundaries. Also, if you like, you take the climatological distribution like values from 1 to 100. So 100 values, not 51. And there the standard deviation will be almost 30. So we're basically giving a context what is uncertain and what is not. And on maps where you see colors, you will see lighter colors of the same type of color, like dark red to light red, as the uncertainty increases in your forecast. In this case, we are around 10, just a little bit below, so the uncertainty is low. Further explanation, there is quite extensive documentation on our GloFAS CEMS wiki page. Please go on and explore it. We have to treat also dry areas, which could be interesting because the zeros, you can't be really rank them. So if you want further information, please go on there. We have this product which shows basin summaries. signal aggregated onto basins. We had it before, in the GloFAS seasonal, but the areas were pretty large, and we didn't have the chance to update the basins to the new higher resolution version for GloFAS either. So this was a wonderful opportunity, so we did that, but we also made it then better, hopefully, and defined more detailed representation with almost now 1,000 basins, a little bit smaller over Europe, where we use the same basins for EFAS, our European sisters, and a little bit larger globally. And we went a little bit further, because in GloFAS, we don't have everywhere points. We call them reporting points. These come from the users. They send their data to us, or they ask for a point of interest to be represented in the model. But unfortunately, there are areas where we just don't have any. So we decided to have at least one basin representative point. So in the sub-seasonal and seasonal, you will have at least that, which will be the highest, the largest upstream area point, which is the outlet. All these basins basically follow the river network. The larger ones we split up. And on the coastline, you obviously have to combine a lot of little rivers usually, but the largest one will be the outlet of it, will be your representative points. So we have these two products. On the left, the one which we call the outlet now, this is the river network summary, if you like, when the rivers, the pixels are colored. In GloFAS, it will be above 1,000 square kilometer. Every single pixel above 1,000 square kilometer will have a signal. So there is no such thing as no signal anymore. Let it be normal, near normal, or low or high, or some level of it. And on the right-hand side is the aggregated one. So you see basically it's kind of an average of the signal at each pixel. Again, everything is based on the ranks and the mean ranks, and then so you average further from the pixels. We have these 5 categories, including the bigger near normal in the middle, and the 3 subcategories in the columns. You see in the middle, that's our legend that you find on the website. So altogether, we have 15 color categories. So the reds will be your extreme low, and so on up to the blues, your extreme high. The reporting points are the same, appearing at the same in the 30-day system. The fixed points are the gray rectangles. There you also can have colored ones when it's about the flood situation, but here there are no floods, so everything is staying as gray rectangle, and the representative points, will be the just like distinguished by a different one, black circles. And just to really show in this small area in the central part of Africa, just few colors, just picking out few colors, and I'm highlighting in the legend basically which ones I'm also picking up. So these are the reds first, so the extreme low anomaly. So really, it's just 10% of the time it should happen. So it's kind of quite large, or small anomaly if you like, with low uncertainty, dark red. Middle uncertainty is higher uncertainty, lighter red, and the lightest of the 3 reds basically will show where the uncertainty is high. And the same with the near normal, so where there is no large enough high or large enough low anomaly, and the dark gray will be showing you that it's quite confident, the situation is quite confident, so uncertainty is low in that it's not going to go higher or lower than this middle 50%. And then the middle one, and then the light one, and then the same with the high anomaly, like 2 examples that you have on this map. So reporting points. This, obviously, as usual, will give you extra information. We provide you with extra information. The same, the top will tell you where the point is, all the metadata about the point. The middle one, the usual hydrograph, kind of similar display, will show you the evolution of the weekly mean or the monthly mean river discharge. I will explain a little bit further on the next slides. And finally, the probability evolution table, which will also show you what happened in previous runs. So what happens in the hydrograph? There's quite a few pieces of information, if you like. Box plot, or box and whiskers, will show you, as this is the standard display in EFAS GloFAS in CEMS, the evolution in the forecast. So from the first to the last lead time. This is the seasonal example, months 1 to month 7, but you can have week 1 to week 5 or week 6 in the sub-seasonal. And you also see on the left something that I call here monitoring truth, but basically it's the nearest to truth by simulating with R5 reanalysis forcing in GloFAS. And this will be also retrospectively added basically after you have the 1 week later, 1 month later, you can go and recheck your map, because this will be added for the forecast part. And then the climatology, that's the background with the major percentiles. The left-hand side will show you the past. This is always the week 1 or month 1, so the shortest lead time. And the right-hand side, will show you the forecast, which is range dependent. So it's really, hopefully, will be consistent with what the real-time forecast behavior is going to be like. And the next one is the tables. So we have all sorts of lots of rows, but this is basically all the forecasts that verify in your latest forecast horizon. Left, you see in different rows the older and older forecast. This is a sub-seasonal example, so every day you have a new forecast. And in the columns, you see all the 7 different anomalies, categories, all the middle ones split in 3, and the groups of 7s will be the lead times. And on top, we also highlight you the expected one, so where the mean of the ranks basically fall, to signpost you basically. And you can expect kind of like going from a light gray, as in this example for the first period, and then it just converges to something either normal, if it basically end up being normal, or in this case, a very wet anomaly. And then even 2 weeks before, the numbers were starting to shift towards the right, so it was a pretty good and high predictability. And the color will be exactly the same as on the Outlook map. So the river pixel that belongs to this reporting point will have the same color, absolutely exactly, as the top latest, most recent row. Where do you find the forecast? For now, for GloFAS, we have the test system, so the stage.globalfloods.eu. We already implemented the seasonal, so you have 2 layers for the seasonal, and basically as we speak, the sub-seasonal layers are implemented also, and we also provide forecasts for previous periods, previous months, and for quite many days for you to basically analyze and see the evolution. Full implementation we foresee by May, hopefully beginning or by mid-May, and EFAS is already implemented on the 12th of March, so you can go and explore. Hopefully you'll like it. And documentation, you have the links. Please send us your feedback and comments, and thank you.
We'll continue now with the GloFAS evolution, next GloFAS evolution. And we will look here in particular, outline to you a little bit what improvements we are planning for GloFAS version 5. And the presentation will be done by my colleague, Stefania Grimaldi from the Joint Research Center. So Stefania, the floor is yours.
Thanks, Peter, and good morning, good afternoon, everyone. It's really a pleasure to provide this presentation about the upcoming GloFAS 5.5 release. I'm presenting today on behalf of a number of colleagues from the Joint Research Center, but also from the CEMS Computational Center, CEMS Hydrological Data Collection Center, and external collaborators from the GFZ Helmholtz Center for Geosciences. But let's dive into the presentation, into all the updates that we are implementing. So we heard it before in previous presentations. The core of GloFAS hydrological forecast is a hydrological model which is spatially distributed and physically based. It's open source and it's open source listlet. I will not explain all the processes because Christelle yesterday already guided you through them. This model, in order to run, needs information about catchment properties and also needs meteorological forcing, specifically total precipitation, average temperature, and evapotranspiration. LeafSpring is a model that can run with different resolutions in terms of space, so pixel size, and also in terms of time. So let's clear first what will be the resolution of GloFAS 5. As you might remember, we had a big jump of resolution, space resolution from GloFAS 3 to GloFAS 4, where we moved from 0.1 degrees to 3 arc minutes, roughly 5 kilometers. I went back. This will stay constant for GloFAS 5. We will keep using 3 arc minute space resolution, roughly 5 kilometers at the equator, and daily temporal resolution. But this is probably the few things that will stay constant, because as you will see in this presentation, there are many, many developments planned for GloFAS 5. First of all is a new big release, meaning that we have a new calibration. Calibration is important to tune the model parameters in order to achieve a better representation of the physical processes in the specific area. We tune the parameters by comparing model results against observations, but we also aim to learn or to transfer knowledge from catchments where we have observation to catchments where we don't have observations. Calibration is an important tool to improve model performance and to provide accurate forecasts, but it's not magic, and it actually must rely on robust model implementation, meaning that the algorithm of the model and the maps that provide information must be accurate. So this is why we actually acted also on the algorithm itself and also on the implementation maps. And I will start with this, with the setup that is with the maps. The catchment physical properties are explained by what are known as the GloFAS static maps. And as a reminder, we provide the GloFAS static maps of all of the current operational release in the GRC data catalog, and we also provide the documentation. But let's have a look to what we will change in the next release. The static maps are a set of 100 roughly maps that provide information about each catchment morphology, land cover, and land use. We have up to 6 different fractions for each pixel, and soil properties. And I would like to put a spotlight here first on the soil properties, because this is a big change that we are implementing. First of all, the total depth of the soil, we changed the definition to make it more consistent with the LeafSpring hydrological model. Currently, the depth of the soil extends to bedrock. In the new implementation, the depth of the soil will extend either to bedrock or to the groundwater table, whichever comes first. Second, we need to have information about the soil properties, hydraulic conductivity, saturated water content, and so on. In early 2023, there was a release of version 2 of a global dataset of soil properties, ISRIC database version 2, and our colleague Francesca Moschini used this data in order to prepare the new soil property maps for GloFAS. The second spotlight that I have here is on water demand. We know that water demand for human use has actually a big impact on the hydrology of each catchment, and we have maps which have been up to date until recent years that provide information on the water abstraction for domestic livestock, energy, and also industrial use. These have monthly frequency, so we can see, for instance, the seasonal variation of water demand for domestic use, or we can also see this interannual or annual variation of water demand for industrial use. Each catchment or several catchments have lakes, which are an important feature. And here we see that the number of lakes which are modeled by GloFAS really increased or is going to increase from GloFAS 4 to GloFAS 5. In the map, all the red points are the lakes that have been added to the database in order to provide a more accurate representation of all the catchments worldwide. The number of lakes actually is double, and the total surface area is almost double. I think that now you're also wondering what is going to happen with reservoirs, because reservoirs we know that they have a big impact on the hydrological regime of rivers. Well, I would like to keep this question on a hold for a second, because a lot of work has been done on reservoirs, not only on the number of reservoirs included in the model, but also in the way that the reservoirs are modeled by the hydrological algorithm. And with this, I would like indeed to move to the improvements to the hydrological model. We repeated several times that it's open source, and there you have the link to the GitHub pages. And you can also reach out to the developers by raising an issue. In this presentation, we will go through all the changes that have been implemented in view of the next big release of GloFAS. We know that GloFAS is a global model, and we know that some hydrological processes are important in some areas and less important in others. This is why in this presentation, we will try to go from general to more specific in order to understand what is the impact of each change. And the first change is actually a change to the mechanics of the model. It's a bit specific, but I think it's a nice way to see how a physically distributed model, which can provide information on all the states and fluxes, can actually be visualized and be analyzed into details to understand whether the discharge output is reliable or not. We mentioned that we have a model with soil layers. Specifically, we have 3 soil layers, and we can also monitor the soil moisture over time for each soil layer. Here in the graph, you see on the top, in the black line is the behavior of soil moisture in the top 5 centimeters. I picked one catchment in a cold, dry area in Russia from memory, just as an example. And we see that it nicely goes up and down depending on the meteorological forcings. Then we have in the second graph the behavior of the soil moisture over time for the 40 years of the GloFAS climatology for the second soil layer, which extends to the root zone. And here again, we see that we have a nice behavior of ups and downs. And now we come with, sorry, I lost it. Okay, now we come with a bit of an issue which was actually raised by some of our users. In some cases, in some specific areas, dry cold or dry hot, and where the soil is really thick, our users observed a negative trend of the soil moisture of the third soil layer. This negative trend was not supported by observations, and actually it was complicating, and it was not allowing adequate interaction between storages. This is why we implemented an improved model initialization, which required analytical solutions to account for the conditions, the climatological conditions, but also the soil properties of each pixel. By implementing this analytical solution, we were able to provide a more accurate representation also of the soil moisture behavior of the deep soil layer, and this allows a more robust model implementation, so more adequate interaction between soil, groundwater, and also rivers. This new initialization has been implemented globally, and it is and we know that it will have a positive impact on the modeling of all the states. Another feature that is important globally is actually river flow. So river flow, we know that can be modeled, is described by the de Saint-Venant equations, and these equations can be solved according to different degrees of approximations. In GloFAS, we used to implement the first degree of approximation, the kinematic wave routing, which is very well suited for steep rivers. But for mild rivers, it has an issue because it might lead to over-prediction of the speed of the flood wave, meaning that the flood wave can come too early, the peak is too early, and also overestimated into magnitude, in terms of magnitudes. Ideally, for mild slope rivers, we should implement the diffusive wave equation. And however, these equations are computationally expensive, and they are not very well suited when we want to run a global model on a daily basis, as we do for GloFAS forecast. To get the best of both worlds, our colleagues of the CEMS Computational Center, and specifically Cinzia Mazzetti, have coded into ListFlood the Muskinghan-Kanch 2D method, which is equivalent to the diffusion method, but is more computationally efficient, is able to model the diffusion of the flood wave, and it also relies on geometrical features of the rivers, so all information that we already had implemented in GloFAS. And here on the bottom right of the slide, you can see the expected result. So we have in black the observed flood hydrograph. In blue, the results of the kinematic wave approach. So you can see that the peak is really shifted too early and is too high, while with the red line, we represent the results of the Muskinghan-Kanch 2D, which has a more accurate magnitude, but also more accurate timing. And I would like to stress that this is actually a problem raised by one of our talks users yesterday, Thomas from Magellan, which observed a lack of correlation in the Amazon River basins. We aim with the Muskinghan-Kanch 2D to improve this condition. And actually, the next slide, we can see also how in technical details we implement this. We want to get the best of both worlds. So we want to use kinematic where it's steep slope and Muskinghan-Kanch 2D where it's smile slope. A pragmatic solution was to create a mask where in each pixel, we know which model is better suited, and we apply that specific model in the numerical solution. The mask is generated by a utility, which is included in the ListFlood utilities. And here we just have a look at how it looks like for some relevant catchments worldwide in both the hemispheres. So in this map, you can see the river network. The red pixels are the pixel where Muskinghan-Kanch 2D, so diffusion wave approach, will be applied, while the blue pixels are the one where we can keep the kinematic wave approach because those are steep slope rivers. Still staying on the rivers, we left behind the topic of reservoirs, and I want to keep my promise now and actually show you the map of the new reservoirs database. In blue, you see the reservoirs that were already included in GloFAS 4. In red, you see the reservoirs that have been added in view of GloFAS 5. You can see that the number is more than double, and now in terms of total storage, GloFAS covers 83% of the volume. But modeling the reservoirs is really challenging. It's not enough to add more reservoirs to the hydrological model setup. We actually need an accurate or a well-suited routine. And the GRC colleague, Jesus Casado Rodriguez, actually did a lot of work to identify the best suited routine for GloFAS. We started off with the current routine. We need to relate inflow, outflow, and storage volume for each reservoir. The current routine works fine, but it has a drawback. Specifically, it computes outflow just depending on the storage volume. And what we observed is that because of this, reservoirs tend to be full, so meaning that they have limited flood control. The work that has been done to look for a better suited routine led to the selection of the algorithm proposed by a paper by Hanazaki, which actually relates reservoir outflow to both inflow and storage. And that leads to a more accurate representation of both outflow and reservoir storage. This routine relies on two parameters, which are related to the flood peak and to the flood volume. And as a novelty in GloFAS 5, these parameters have been estimated outside of the hydrological model. They have been estimated using random forest regressor, and as explanatory variables have been used climatological variables, but also the features of the reservoirs themselves, the characteristic of the dams, and water use. And in training dataset, a number of catchments from USA, Mexico, and Brazil and Spain have been used. Still staying on the rivers, we look now at a different physical phenomenon. which is called transmission losses. Transmission losses are the loss of water volume, which happens in a river as it travels downstream due to evaporation, transpiration for vegetation, and also seepage through deep groundwater. Generally speaking, these transmission losses mainly happen on arid areas, and here in the map on the top right, you see highlighted the aridity index, so the red areas. However, very recent papers show that this phenomena is happening and has been observed and measured in many other areas worldwide. In this slide, we will see an example of application, and we will try to explain why we thought it was beneficial to include this phenomena into the model. We specifically look at a case study in the Horn of Africa, and here in the graph you see in a time series of discharge. In black is the observation. In red is the model prediction. As you can see, the model is not doing a good job in repeating or replicating the observation. There is a general overall overestimation of the model, and we then look at the full time series of also of the states, and we observed that there was something weird happening in the soil moisture. Specifically in 97, soil moisture of the soil layer was increasing abnormally, as if a lot of water was soaked by the soil. We looked a bit historically, and we found out that there was a big flood in the area in the 97, which was apparently absorbed by the soil in the soil layers of our model, but not seen in a discharge, meaning that the model was missing process representation, and for this reason, it was trying to compensate for it, leading to missed events, leading to negative results. By including the transmission losses into the same model setup, we were able to actually get the flat peak in 97, a better and more accurate representation of soil moisture, and in the bottom part of the slide, you actually see the model comparison for the recent years until end of 2023, where the black is the observation, the red was the result of the model without transmission losses, and the blue is the result of the model with transmission losses. Not perfect, but a much better reproduction of the real state of the catchment. Finally, a few small adjustments, and then I can move on with the calibration. So there are a few small adjustments that we did also in very specific areas, and here you see the title is about snow. So we talk about pixels in very high areas. I know that it's really hard to see the yellow pixel, so I will do a zoom in. And in this pixel, we are accumulating snow. It's the pixel constantly covered by snow. And when we compare these areas of the results with a global database of glaciers, we could see a very good matching, which was satisfying. But at the same time, the colleagues of the GFZ Helmholtz Center for Geoscience reported that some pixels showed an over-accumulation of snow. Snow was just accumulating over and over again, and this was not consistent with their observation of global total water storage. So they suggested a pragmatic approach to improve snow melt, to increase snow melt and snow ablation, and we did collaboration. We collaborated with them, we did testing, and we observed that the proposed change was removing the issue while keep preserving the performance in terms of prediction of hydrology. Finally, we are well aware of the limitations of list flood. For instance, at the moment, list flood is not capable of modeling horizontal fluxes in the groundwater. However, we need to account for this limitation when we model water abstraction for human use, because people take water out of the wells in order to satisfy their needs. By taking into account how the model works, we were able to identify a good solution that also allows a more robust model setup. And here in the bottom slide, we have an example of an catchment in Israel, where again, the black is the observed, Without fixes, we had in red, we had an overestimation of the low flow and an underestimation of the high flow. With the fixes, we actually achieve better better representation of the observed discharge data. We needed to do a cutoff of all the model improvements because we wanted now to run a calibration and actually deliver a new operational version to our users. So model calibration means that we tune least flood parameters up to 12 least flood parameters, leveraging on observations. The observations are in situ discharge observations. And in this map, we see, for instance, in the blue dots are the gauge stations in Australia with the upstream area in colors. In these catchments, we use the tool that we use for GloFAS 4, and it's a parameter search algorithm based on the distributed evolutionary algorithm for Python, which has been, however, largely improved in order to pre-select the parameters. We don't calibrate the snow melt coefficient when in a catchment where it doesn't snow. We use a longer time series according to the recent research findings, and we also use a more restrictive stopping criteria for the selection of the best individual. The evaluation is based on the modified KGE, but we also look at low flow and high flows and also the evapotranspiration, because GloFAS is used by CEMS floods, but also by CEMS drought for drought monitoring and prediction, and also to analyze water resources. But what does gauge catchment in GloFAS 5 means? Well, a catchment is defined gauged in GloFAS if we have in situ discharge data, if the catchment has at least 500 square kilometers upstream area, and at least 4 years of data of good quality. Of course, there will be areas without data, which we need to deal with. But let's first see how we tried to minimize the areas without discharge data. GRC colleague Giuliana Disperati, in collaboration with the CEMS Hydrological Data Center, collected as many data as possible. At the moment, the global database includes over 60,000 stations. Not all of them, however, can meet the criteria to become a gauge station used in GloFAS calibration. We used 2,000 roughly calibration stations in GloFAS 4. There will be roughly an increase of 50% for GloFAS 5. Let's look at the example of Africa, where we had an increase of stations from 420 to over 650. In the map, you see in blue the areas which were already calibrated in GloFAS 4. In orange, the area that have been added in GloFAS 5. So we have also a lot of areas that in the zoom in the coastal areas and in tiny catchments. But I would also like to stress that when we don't increase the total calibrated area, we actually increase the number of stations inside the catchment. And for instance, this is an example, the Limpopo Basin, where we had 17 calibration stations in GloFAS 4, 62 in GloFAS 5, meaning that now we actually are able to analyze and to verify the model behavior in the upstream areas to achieve a more robust calibration. And in the bottom graph, you can see that with GloFAS 5, we have a shift of the upstream area towards smaller values, meaning that we can really look at how the catchment behaves from upstream to downstream, looking at all the details. Now, despite all these efforts to include as many stations as possible in the global database, there are still areas for which we don't have gauge data. And in these areas, we need to estimate the parameters somehow. So in GloFAS 4, we used a pragmatic regionalization approach, which meant that we were transferring the parameters from the catchment, which was the most similar in terms of climate and in terms of geographic proximity. In GloFAS 5, we aim to improve this approach by using parameter learning. This development is led by Carlo Russo, a GRC colleague, and it entails two main steps. First of all, we need to build a surrogate which replicates the behavior of least flood, so which learns how least flood models discharge based on input meteo and the input attributes of the catchments. The surrogate has a key feature, it's differentiable, meaning that it can be readily used in a machine learning, parameter learning algorithm to map physical properties and methodological input with least flood parameters. But now I think that you are all waiting for some result and see what is the outcome of all these improvements. And I will try to do so in the last slide actually of this presentation. The calibration is just running right now, so we are happy to share the results that are coming through. We use as example the Limpopo Basin, and which has a little bit of everything. It has MCT pixels, it has lakes, it has reservoirs. In the map here, in the dots, you see the value of the modified KGE. On the right, on the left side is the results of GloFAS 4, so the old model, and on the right, you have the results of GloFAS 5. The colors go to red to blue, with red lowest performance, blue highest performance. I would like also to mention that some catchments were already calibrated in GloFAS 4, which are highlighted by the black arrows. We can see that there is a shift from red to blue, meaning that there is an overall model improvement in all the stations. And as a summary of this improvement, we can have a look at the maps on the right, where on top we have just the difference in terms of modified KGE, red where we have a degradation, but green and light green wherever we have an improvement. And we see most of the points are actually light green or green. And we also look, in this catchment, we had a lot of overestimation, so we reduced a lot of the bias, but we also looked at the improvement in terms of correlation. And here again, wherever you see a green or dark green point is an improvement, wherever you see a red point is a degradation. We can conclude that the results so far are encouraging. The calibration is running right now. So the next step are actually continue running the calibration, delivering the climatology. We aim to have the climatology available from the early warning data store in Q3 2025. Then, as usual, we will implement the operational setup first on stage for 4 weeks, and then eventually on the official GloFAS website. The timeline, precise timelines, will come in the next weeks, months. We will publish news items on the global GloFAS website, so stay tuned. And I'm sure that you also have suggestions and requests, and you also notice something that we can further improve and which was not included in this presentation. So please also take the chance to share your ideas in the survey.
Thanks a lot, Stefania. That was a lot to digest, definitely. And yes, as everybody could see, this is a massive work, a massive team and collaboration work, which is promising for the moment. So it looks really good. We are really confident that the next version, GloFAS version 5, will be, again, a major step, provide a major improvement in forecast skill. So stay tuned for updates. We will continue now to show more and more results also in upcoming conferences at the EGU or Living Planet Symposium. And then, of course, as soon as we have something available, we'll share this as a news item on GloFAS.
Welcome, everyone, to this interactive session. It will be my colleague Gurpreet Das from the CEMS Flood Computational Center, and my name is Nina Bossert from the CEMS Flood Dissemination Center. We also have a colleague, Conrad, in the background, who will be answering any questions in the chat. So here we do not have this question and answer thing in the breakout room. Yes. First slide will be on, we'll show you the Menti, a link to the Menti and a Mentimeter. Some of you might be familiar with it. Some of you have probably never used it. We will, during this interactive session, repeatedly have small polls or questions where we would like to collect your view. And so we would like everyone to get ready. You can use either your phone with a QR code, scan it, and then you will be directed to the web page, or you go there directly. You can use your computer as well and enter the code. And this will reappear when we have the question. So if you did not manage to log in now, don't worry. This will be reappearing. But let's get started then with the presentation itself, or the interactive session itself. I'm trying to forward, but it's not working now. Okay, thank you. So I see it's not yet. I lost the possibility to control the presentation. I think maybe now. Okay, now. So the GloFAS Map Viewer is probably the main tool to access GloFAS forecast data very easily. And if you're completely new to this, you can go to this homepage, global-flood.emergency.copernicus.eu. Very easy to remember. And then you will find a little further down, you will find an icon where you can click and be directed to the map viewer directly. And then you will see a global map. And if it's the first time that you're logging in, it will be empty. Otherwise, you will see the last saved layers that you used. And let's now imagine it was the 3rd of February, 2025, so quite precisely 2 months ago. And you opened the GloFAS Map Viewer to assess the current forecast, and you're interested in Australia. Which was a coincidence with the previous short talk on the flooding in Australia, and this is the setting. So imagine that you want to make forecast for Australia. Now the question is how you can get a better idea of the current flood situation using the GloFAS Map Viewer, and this is what we are going to go through and present here in the next 30 minutes or so. And before we go further into it, we will look at the first Menti question. And here you see again the QR code, and you can see the login or the code for the login if you go to menti.com directly. And we have a number of users here already. I think I will start the question now. If you don't manage this time, don't worry. We will have more questions, and you can log in for the later ones as well. So let's see what the first question is. It is about your experience level. We would like to get to know you a little bit better, and we would like to rate your experience level. Are you an absolute beginner with the GloFAS Map Viewer, or have you clicked around a bit already? Are you using it regularly, or do you know it by heart? Maybe you need to scroll down if you're using your mobile phone. The graphic is probably a bit too large, so you can scroll down and then you will see the alternative answers. And soon we will have a better picture of you. Okay, quite a diversity. That's nice. And as Peter said, I mean, it is probably more suited the presentation is for beginner users, but we will have certainly some functions, some features that you have not known before, and maybe new ideas of how to use the layers. So thank you for that. Next will be Gurpreet presenting several features of the map viewer.
Thank you, Nina. So I'll give you a little walk through the GloFAS Map Viewer interface with maybe a few features you may not know about or that you may not be using now. So here we have the interface with here a few layers loaded. So we have the layer window with the reporting points and rapid impact assessment layers loaded. So here we have an eye in a green circle, and if you click on it, you have a pop-up window that appears, which gives you information on the layer. And if you scroll down, usually you also find a link that leads you to online documentation, which tends to be more detailed. And on top of that layer window, you have a date, which is the date of when the forecast was produced. By default, it is going to be the date for the latest, most recent forecast. Now, let's say you want to have a look at an older forecast. You can use the yellow arrows to go back and forth. But if, for example, you want to check the forecast that was like 2 years old, it can be quite a lot of clicking. So a shortcut could be to click on the date, and then you have a window that appears, and then you click on the month and year, and you can select the year. And then when you select the year, you have another window where you can select the month and finally the date, the day. So now we have the forecast that was produced on the 11th February 2023. So if there was a shortcut to go back in time, there is one to come back to the latest forecast. You can simply click on the blue clock, which will lead you automatically to the most recent forecast. Now, GloFAS has a global coverage, but you will certainly want to have a look at a specific country or region. So usually you can zoom somewhere, zoom in and out using your mouse wheel or the slider. And if you want to go back to the global view, you can click on the G, which stands for global, and you'll be led back to the global view. Now we'll move to the other side of the interface, and you have a few tabs. One of them is the search tab, and which allows you to look for a specific river, location, or region. Let's say we're looking for the Burdekin River. So we enter Burdekin and we have a few options that appears, a few locations and one river. Because we were looking for the river, when we click on the river, it will lead us to the Burdekin River. Another interesting feature is the map background, which allows you to change the background of the map on the interface. So you have a list. For example, here we change it to the satellite background, which can be quite useful because sometimes you have a few layers that show up better on certain backgrounds, or just because you prefer a different background. And a little sneak peek in another interesting feature that we cannot go into detail. Today, the external WMS tab on the top part, it allows you to add external layers through a WMS into the GloFAS Map viewer to, for example, compare GloFAS to external information. And just like that, you can set up your own interface. Because all the layers you will load, the background you'll select, the external data set you'll load into GloFAS Map viewer will be as you left them the next time you log in. So you can set up the interface for a region of interest, and each time you log in, you will come back to the same setting, and so GloFAS will be ready to use. So now we have the second Menti question for the presentation. For this little session, you can scan the QR code, join the Menti. So you go to menti.com and enter the numbers here. So what is your favorite feature and are layers of GloFAS Map Viewer? You can enter, is it working? Yes. You can enter a layer, for example, reporting points, or I don't know, flat summary, a feature, the zoom feature, the background feature. And in case you cannot join the Menti for connection problems or any other issues, you can always put your answers in the chat. Okay, so reporting points, new seasonal outlook, long forecast archive, flat summary layer. There are a few layers we'll be talking about, so it's a good news. Okay. The thing is, we unfortunately have time constraints, so I don't know for how long. Maybe, what time is it? Yeah, maybe we should move on. Thank you for entering your favorite features and layers. Keep on answering, maybe in the chat, but unfortunately, we will have to move on to the next part. Nina.
Okay, let's see if it works. No,
No?
I will send it again. Maybe this. Okay. Now I should be able. Yes, exactly. Perfect. So now we will have a look at a layer, a quite central layer for the hydrological forecast, and it's the reporting point layer found under the hydrological menu. And we can see that something is definitely going on in Australia. So if we zoom in a little more to see a little bit better, we can see there are several kinds of reporting points in different shapes, different colors. And first we will look at the shape itself. So you will see that there are upward pointing triangles and downward pointing triangles, and also circles, which are not shown in the example, unfortunately, but there would be circles as well. And the shape of the reporting point tells us something about the trend of the discharge forecast using flow for rising flow using the upward pointing triangle, falling flow, downward pointing triangle, and for constant flows, the circle is used. And if you look a little bit closer, you will also see that the outline and shading of the points differs. And this tells us something about the timing of the peak. You can interpret it like that. The fuzzier the signal or the visualization, sorry, the further ahead in time the peak. So for example, no outline and a pale color, the peak will be further or later in time. So we will do a quick test here. First Menti on the reporting points, and some players are ready. So if you went back from Menti, you can just log in again at menti.com and enter the code or scan the QR code. And I would like to ask you, the audience, which area do you think is experiencing the highest flows at the moment? Is it that central Queensland area where the flows are rising, which is area 1, or is it the eastern coastal Queensland where the flows falling, area 2, or do you think it's not possible to tell based on what you just learned? So the shape and the coloring of the reporting points. Let's see. And maybe I can also add, there's no really right or wrong. Unfortunately, it's still looking like that. But all answers are equally likely. You're completely right to saying area 1 or area 2, or you're not possible to tell, because it's actually there is more information hidden in these reporting points, and we are going to look at more details here, and maybe then you will have a better idea of how to interpret these picture. So another very central and important information is actually stored in the color of the reporting points. And the color tells us something about the severity of the flood signal. And it uses the concept of return periods. You might be familiar with it. If not, this is a statistical measure that shows how unusual, and that means how high flows are in a specific catchment. So purple in this case would be more unusual, higher flows for specific catchment. The yellow, less high flows. And finally, there's also the number next to the reporting point, showing the percent probability for a certain flood category, so 5 or 20 years, to be exceeded. And the higher the number, the higher the likelihood or probability that this event might occur. And there is even more detail in these reporting points. So we saw now all outer features, so to say, but then we also have a pop-up window. And if you click on one arbitrary reporting point, you will see a lot of information. But among them, maybe the most important one is the hydrograph, forecast hydrograph, and we saw that earlier today in presentations as well. So here you can see the whole forecast period of 30 days, and you can see how the discharge is developing over the time, and you can also see something and quite useful, which is the uncertainty or certainty, if you look at it the other way around, of the flood signal shown by the box plots. Let's see. For each time step. So you are maybe aware, because also this was mentioned earlier in presentations, but GloFAS does not only provide one forecast, one possible forecast, so a deterministic one. No, GloFAS provides probabilistic forecast or ensemble forecast. And Irvin said that number earlier today. We have 51 different forecasts actually, and the box plots are a summary of these spaghetti plots, or that you saw yesterday maybe as well. So the 51 forecasts are combined to statistical measures like the median and percentiles and shown as a box plot. And the small spread of the box plot means a low uncertainty or high certainty, and a large spread means a high uncertainty. So in this example here to the right, you see that this forecast stretches really from no flood at all to extreme high floods, and this is really that's really no information. You cannot really tell what's going to happen. So next and final question on the reporting points. Nice that several players are there already. You can wait a few seconds just. Okay. So based on this additional information now that you received, would you change your previous assessment with this information? So would you now say, for example, oh no, that's probably the other region that is more, that's experiencing higher flows at the moment? Or do you think that you still don't know and are not able to tell? And again, you might have to scroll down a bit on your mobile if you're answering on the phone. And there's really no right or wrong, but probably Menti will show you that some of the answers. No, here everything is right. And that's correct, because I mean, this is a really a personal judgment, and I can answer it also. For me, I would not have really enough information yet. I would like to see more reporting point pop-up windows, for example. I would like to understand how several rivers and water or catchments in the area behave and are evolving. So thank you for answering these questions. Gurpreet was now going to present another way of showing the forecasts, the flood summaries, exactly.
So now we will have a look at the flood summary layer for 1 to 30 days, because GloFAS can give you a forecast for up to 30 days. You can load the layer from the hydrological tab. And when you load the layer for Queensland, Australia, so the area highlighted by the reporting points, we can see that we have rivers highlighted in yellow, in purple, and red. The color is the same color code as the one used for the reporting points, so it refers to return periods. Yellow 2-year return period, red for a 5-year return period, and purple for a 20-year return period. And instead of numbers, as for the reporting points, the likelihood is represented by the shade. the darker the shade, the higher the likelihood. So here we can see that there is a 20-year and 5-year flood signal in the northern part of Queensland. When we do flood forecasting at a global scale, we usually tend to focus on areas highlighted in purple and red. Now, with flood summary, you can also have a look at the forecast for sub-periods. So we will load, again, in the hydrological tab, flood summary for days 1 to 3, 4 to 10, and 11 to 30. Okay, so here we have Queensland for the layer flood summary for days 1 to 3, so the forecast for the first 3 days of the forecast period. And we can see that there is a 20-year flood signal in northeast Queensland near the coast. And now if we look at the forecast in 4 to 10 days, we can see that that 20-year flood signal is moving to central Queensland. And finally, in 11 to 30 days, we can see that the flood signal moved more westward in Queensland. So flood summary can be used to visualize the forecast in a different way, spatially. So the question would be, now that you know a little bit more about reporting points and flood summary, is, let me start. To assess when and where flood is forecasted, would you prefer to look at reporting points, flood summary, or both layers? And for each question, you have about 30 seconds. As Nina mentioned, you can scroll down in case you cannot see the options. And there is no wrong or right answers. Maybe we should have had an option saying none. I don't know. Okay, 5 seconds, almost there. Okay, so a lot of people would use a flood summary in both. That's interesting. That's good to know. Thank you for letting us know. And now we'll move to Nina again. Nina, over.
Okay, thank you. Exactly. We would like to present some kind of a different type of forecast layer, focusing more on the potential impact of the flood inundation. And this layer is found under the flood risk menu called Rapid Impact Assessment Layer. And it colors larger administrative areas according to the maximum flood impact forecasted for the 30-day forecast period. Let's see. Yes, and if you click somewhere in the colored area, a pop-up window will open up showing a risk matrix, categorizing both the likelihood on the y-axis and the severity on the x-axis for an event. And the earlier an event, the more likely it is, and the more people affected, the more severe it is. So far, so logical and easy to understand. And these two are then combined to a combined risk of, in this case, a high risk colored in or shown by the red color. And you will also have in this pop-up window exposure information. For example, the number of people affected or the extent of surface area inundated. And you might notice that we have a protected and an unprotected scenario here. And instead of explaining what these mean, I would like to ask you in the next Menti. Let's see. So, question is, what does the protected scenario mean? So the definition of a protected scenario. Does protected scenario mean that it takes flood defenses into account, or does protected mean that it assumes 10% of the population can be evacuated in case of flooding? And here actually there is a right or wrong. So you better think twice. Curious to see the answers. Okay, nice. as a group, collectively, you answered right. This is perfect. It is indeed the correct answer is that the protected scenario takes flood defenses into account, which means that if a region is assumed to be protected for a flood with, let's say, a 20-year return period, then no flood impact is going to be computed, and the area will not be colored here, because this is also important to notice. The rapid impact assessment is based on the coloring of the region of the the coloring of the region is based on the protected scenario. I'm sorry. There is another layer here to examine, which is called the rapid flood mapping, because to do the impact assessment, one needs to have some kind of inundation forecast. And in this rapid flood mapping layer, the inundated area is computed based on the maximum forecasted flood level. So it's kind of a worst case scenario. And it's quite a high resolution. We heard earlier in the beginning of the session that it's not as high as in other tools, and that's certainly true, but it's still 90 meters globally. So pretty impressive high resolution for a global application. And when zooming in, like here a little bit more, you can see this area highlighted by flood extent. So it's not, in fact, the whole of Queensland that is it's experiencing flood impact. It's more concentrated in this area here. And let's see. Yeah, just to highlight again, this is really kind of a worst case scenario, and this rapid impact, rapid flood mapping layer shows you where in your larger region you should look for flood impacts and maybe send warnings. That was all on the rapid impact assessment. Gurpreet is now showing something on the hydrological model performance, which is also available in the GloFAS Map viewer.
Okay, so now we'll be loading another layer, the hydrological model performance layer that you can find in the evaluation tab. So this is one of the features that sets, I would say, slightly GloFAS apart. You have access to the model performance information freely, and I would say in a quite user-friendly way. So when you load the layer here again in Queensland, Australia, you can see that you have a few dots that appear in different shades of blue. So the color represents the KG, which is a performance score in a way. It's how well did the model performed when compared to observation data over the period where observation data was available. The closer it is to observation, the darker the point is, and the more poorly it performed, the lighter the dot will be. Now, if you want to have more information than that, you can click on one of the dots and you can see the three components that make up the KGE. We'll have a look at all of them one by one to see what information they provide. So first we have correlation that will give you information on peak timing to know if GloFAS tend to forecast correctly the peak timing. Is it late or miss it or information like that? Then you have the peak magnitude, which is given by the bias. Does the model tend to overestimate or underestimate river discharge? And finally, you have the variability that will give you information on the peak frequency. So now, how can you use the layer? You can use it just to have an overview of the situation for your region. So you just first look, do you have points in the area? And if so, what color are they? And if you're more interested in a specific river, maybe you can click on it and then have a look at the different components of the KGE to have a better understanding of the uncertainty. So here we do have a few points that tends to be dark or medium dark, so the model performs decently well, but we can see that in central Queensland we have actually no points. And the reason why we don't have any points, it was mentioned by Irvin in his presentation, it's we receive data, observation data, and this is how we're able to compare GloFAS to observation data and estimate uncertainty. So a big thank you to all the people, organizations, institutions that have been sharing and are sharing data with us to help us improve GloFAS. Now, the good news is that if you want to add more points in your area and you have river discharge observation data, you can share it with us if you would like to through the contact form available on the GloFAS website. You can go on the GloFAS website, scroll down, click on contact, enter your name, mention that you would like to share river discharge data for which area and over which time period, and one of our colleagues will come back to you. So thank you for your help. Now, question time again. Okay, almost there. Let's start. Again, you can join the Menti through the QR code or the use code on top. So would you change your forecast assessment based on the model performance layer? So here you have the flood summary layer. On top of that, you have the model performance layer, and that's all you have. Would you change your forecast based on that new layer? Okay, there is no right or wrong answers. Okay, almost there. Okay, interesting. For people who answered yes, if you would like to, feel free to put why, if you want to, in the chat. Okay, so there is now another way to estimate uncertainty that Nina will present. Nina?
Yes, thank you. Let's see. You can forward the slide. Yeah. Yeah, we wanted to show you two layers as well that show you the impact of reservoirs. And the first one is a layer showing just the location of lakes and reservoirs that are included in the model setup. And zooming in, one can see names as well. It's basically not possible to read here, but it's they are there. And it's also important to note that these are only the largest lakes and reservoirs that are integrated here. So globally, we have around 460 lakes and 670 reservoirs included in total. So definitely not all rivers and lakes, reservoirs and lakes. But still the largest ones are there. And we also have another layer called the reservoir impact layer, and that is showing for each pixel along the river the potential impact of the reservoir on the discharge. And the higher the number, the darker the color, the higher the impact of the reservoir on the discharge, and consequently also the less reliable the hydrological forecast, because the forecasted flood might be altered completely through storing the water in the reservoir itself or releasing water while we do not see anything during dry time. So it can alter the discharge. And if we now look at our current situation, we see that actually only this reservoir up here lies within the affected area, and it's the Burdekin Reservoir. And you see the light gray color here. Probably before you might not have even seen it, but there's light gray color. And question is now, if this information would change your mind, and if you would rate the reservoir impact on the flood situation like either low, medium, or high, and consequently maybe reconsider how you, in which way you assess the flooding situation. So reservoir impact low, medium, or high. Yeah, and we put a right answer here. It's maybe probably not super scientific, but still, I mean, you have the reservoir impact of 0.5. It's a ratio, so 5% of your discharge could be altered through the reservoir upstream here. And we as forecasters would rate this this color as low. But of course, I mean, it depends on your application, and you're allowed to rate it as medium or even high. Yeah, that was a lot of information that we went through, and Gerprit is going to be summarizing a little bit this case here.
Okay, so I don't know how much time I will have. I have 1 minute left. So it's just a recap of the forecast. We highlighted the area at risk, Queensland, Australia, that there is a 20-year return period, flood peak that is expected to move from northeast Queensland to west Queensland over the forecasted period. And there is a high risk, and the uncertainty is high in central Queensland, but there is a low uncertainty in northern Queensland with limited impact of reservoirs in the area. I think we will have to stop here before we're just all moved back to the main room. Do not hesitate if you have any questions for us. Okay, we have 30 seconds. Yeah, so thank you very much for attending this session. We may try to answer the questions when we will be back to the main room. I don't know.
My name is Mohammed Azhar, and I'm a hydrological data analyst at ECMWF. And in this session, I will walk you through a couple of Jupyter notebooks and show you how to access and download GloFAS data from the new CEMS Early Warning Data Store, and 2 other notebooks which are a little bit advanced, but don't worry about it. We will go through them. The second one is showing the best practices to download the GloFAS data via the EWDS. And the third one will show you how to map your observational discharge goal station to GloFAS grid cell. And please, if you have questions, feedback, or comment, don't hesitate to contact me at this email. And during the session, please ask questions and write to the chat if something is not clear for you. Okay, I will start with the part 1, which is accessing and downloading GloFAS data from CEMS Early Warning Data Store. And in this notebook, I will walk you through the basics of the new data store, including how to create an account, how to access data through the EWDS, use the Python API, and use the new package AirKit to access and process the data. And finally, show you how to get support if you have a problem using the EWDS. We will start with creating an account in the new data store. And please, I'm asking Karen to share the 2 links with the participants. The first link to the Jupyter book and the second one to the EWDS. So you can click and try with me what I'm showing you in the Jupyter notebook.
Yeah, so the links are in the chat.
Thank you, Karen. I suppose you have the links, and let's start. The new EWDS, the Early Warning Data Store, provide free and open access to GloFAS data. And to download data, you have to create an account in the data store. And previously, if you had an account on the legacy climate or atmospheric data store, the CDS or the old CDS, those credentials will no longer work for you. You have to create a new account within the ECMWF. And you should use this account to access EWDS. And to do so, or if this is the first time you have visited the EWDS, you'll need to register by clicking Login Register in the top right-hand corner. I will show you in the website directly. Login and register. I have already an account, so I will connect directly, but if you don't have an account, you will be redirected to the ECMWF to create an account. And you can do it now because it will take only 1 minute. It It's pretty fast. You can try it now. And if you have a problem, please write in the chat. Okay, so I suppose, and you can explore the website, or you can explore the data store without an account. But to download data, you have to connect to the store. So to access data through the EWDS, you have two choices. Right in the search bar, your data set that you want to download, or like you can see in this capture, or I will show you directly in the website. Click on dataset and write, for example, GloFAS forecast, and the result should look something like this. The first result is the GloFAS forecast, and to download the data, you have to click on the title of the dataset, or you can use the filter in the left corner. As you can see here, you can select, for example, product type forecast, provide the Copernicus CEMS, the coverage global for GloFAS, and then you will see the data set that you want to download. And please try this, because it's really simple. Try this on your side. All right, so I suppose you have reached the river discharge data. So if you click on it, this will take you to the download form, where you can manually select the data you are interested in. And we will go through a simple example. All right, this example, let's suppose we want to download the river discharge for Australia. And the selection should look like something like this. The system version operational, hydrological model is flood, product type, variable, year, month, day, and the lead time hour, which will appear really simple in the download form. I will show you directly in the website. Okay. You select the operational or the system version, and you will find also the legacy version. If you are interested in the legacy version, you can select any legacy version you would like to see. Okay, let's suppose we want operational. For the hydrological model, you click on list flood, product type, control, or ensemble forecast. Let's say we want control forecast. For the variables, we provide 4 variables: river discharge, snow depth, water equivalent, runoff water equivalent, and soil wetness index. In this example, let's say we want to download river discharge. And for the year, maybe we want today's forecast, because it's already available in the EWDS. Click on 2025, April, and the 3rd of April. For the lead time, you can select only one lead time, or you can select all. Click in select all. And for the geographical area, we want to download only Australia. So we have to click on subregion extraction and change those coordinates. So let's go back to our notebook, and those are the coordinate that covers the Australia. So we will go from -9 to -39 north south. And 109 to 154 west east. And that's it. The final step is to select the data format that you would like. We provide 2 data format, GRIP2 and NetCDF, and also the download format, which is zip or unarchived. Let's select a zip file. And finally, you have to click or to accept the terms of use of the data. and you can click on Submit Form to submit your request. I hope this is clear. And when you click on Submit Form, this will take you to your request page here, which can also be viewed at any time by clicking your request in the top right of the website. Let's go back to the website. Here's the button. You can click on it, and it will redirect you to your previous request. Okay, so in this page, you can see the status of your download, if it's code or ready to be downloaded, or in progress. So you can see here the data is in progress, and when it's ready, it will turn to a green button, complete, and you can download the data by clicking download. And here's your data ready to use. Okay, that's the first way to download GloFAS data using the website or the web form. And there are other ways to download GloFAS data. And the most important thing is the API, which is really useful. We provide a Python API, which is a programmatic access via a programmatic access to the data. And in this example, we will be accessing data from the EWDS with the CDS API Python package. And you can click this link here if you would like to learn more about the CDS Python package. And please, if you get stuck while following this tutorial, you can follow more detailed instruction on this process at this page. While logging into your EWDS account, you can visit your profile page by clicking your name in the top right of the EWDS, and to locate your API token, because we will need this to create a file which is necessary to use the API. So I'll show you in the website where to find your API token. You click on your name in the top right corner, your profile, and you will find the API token here to use for accessing data through the API. So click on copy your API token, and we will use it later. I'll show you how to do it. Next, we'll need to create this file, .cds API. By default, the CDS API use a file in your home directory. This is the directory if you're working with Linux, and for Windows, it should be equivalent to C users and your username. The following code block will create or change the file for you. You should update the API token with your personal access token. And first of all, if you don't have PyYAML installed, please uncomment this line and install the PyYAML. And after that, run this cell in your Jupyter notebook. And just a reminder, you can download the Jupyter notebook from this button, and you can try it on your own. So you just have to put your API token that we copied from here, from the EWDS website, and put it here, and then this code will create the file for you. You can try it now, and if you have a problem, please write in the chat. All right, let's move on. I suppose you have already created the file using this code, or you can do it manually. It's the same, but it's a bit simple to use the Jupyter notebook or this code snippet. Okay, let's make a request with the CDS API. First of all, you need to install the CDS API package by uncommenting this line. Okay, so everything is set up now. We have to, and we can download our data using the CDS API. The first thing to do is go back to the EWDS, go to your request, click on details and open request form that we did already. In the bottom of this page, you will find this button. If you click on it, it will show the API request code. It's the same thing that we did in the form, but it's in form of a Python code. So copy the code and put it in your Jupyter cell. And finally, call the client.retrieve method of the CDS API package and give us parameters, dataset, and the request download, and it will do the work for you and download the requested data. And after running this cell, you can go back to the EWDS, your request, and you will find your request here. And you can check and monitor the status and finally download. I hope everything is working fine for you. If you have a problem, I remind you, please write in the chat. The last part of this notebook of the part 1 is accessing data, store services data with EarthKit, which is a new developed package within ECMWF, and it's free for use. You can download it and use it. Okay, let's continue. EarthKit is a Python package which provides tool for accessing, processing, and visualizing Earth science data. It also offers direct access to the Copernicus data store and speeding up the process of getting data from the stores. And you can use it within the EWDS, the CDS, and the ADS. If you do not already have EarthKit data and EarthKit plot, in this notebook, we will not use plot. We will use only EarthKit data, but go to EarthKit documentation and you will find other useful tools to use. Okay, let's install the EarthKit data and EarthKit plot and comment and run the following cells: pip install EarthKit data and pip install EarthKit plot. And now we are able to use the method from source to make the same request we made earlier to the CDS API. Let's see how to do it. It's pretty similar to the API. One thing that we have to change in our previous code, which is the method to download data. As you can see, we still have the same data set and the same request, but you have to change those 2 lines. I'll go back to the API, client CDS API, client CDS API dot clients and client dot retrieve. You have to change it with this method. And after that, your data will be in this variable, and you can work with it directly in the Jupyter Notebook. And we'll, by, for example, convert it to X-ray and print it. You can do whatever you like with the data. One advantage of using the EarthKit instead of the CDS API is that the object returned from our request can be immediately opened and explored with commonly used scientific tools like X-ray. Finally, for help concerning any problem you encounter while dealing with EWDS and CEMS data, please raise a request here. I'll show you in the website directly. Okay, you can raise a ticket to our teams to help you with your problem dealing with EWDS. Contact us, click on it, and raise a ticket. Okay, I hope this is clear for you and you were able to follow with me and explore the EWDS website. Okay, now I will move to the part 2. In this part 2, I will talk about, or I will show you the best practices to download GloFAS dataset. We provide 5 datasets in the EWDS: GloFAS climatology, GloFAS forecast, reforecast, seasonal forecast, and seasonal reforecast. So let's suppose you want to download a long period of data and not only one specific date. You want to download a long period, so you have to use the API and you have to learn some tips and tricks about how to better use the API to download your requested data. The EWDS retrieval times can vary significantly depending on the number of requests that EWDS has at any one time, and also based on the following factors that affect GloFAS. And those factors are the priority of the dataset in question, the size of the request, the number of requests submitted by a user, the request to retrieve data from ECMWF archive, the number of requests for a specific dataset, and finally the size of the overall queue. And if you want to see the status of the EWDS, you can go to the EWDS and click live. And you can see how many users are currently downloading data and how many requests are running and how many users are waiting. So if you have a problem, please go back to live and see what's happening behind or in the background in the EWDS. Okay, in this notebook, I will show you one example per datasets and what is the best way to download the data. And I want to remind you with one important thing, which is the EWDS is not operational service and should not be relied upon to deliver data in real time as it is produced. Okay, let's start. In the first cell, we import all our packages needed or that we will need in the following cells. We will set up our directory where we will download our data. And let's start with the GloFAS climatology. The best way to download GloFAS climatology is to loop over years. So you will download one file per year. And you can monitor the status of your download in the log. It will show you downloading data, the percentage of the downloading, if your request has been updated to accepted or to successful. And you will find your data in that directory that we defined before. So the best way to retrieve GloFAS climatology is to loop over years. So please download those notebooks and use them for your use cases. Okay, let's move to GloFAS forecast. The best way to download it, or the best practice to download the GloFAS forecast, is to loop over years, months, and days at the same time. I'll go through this code a little bit and explain to you what we are doing here. The first part is to define a function to compute the date ranges, and after that we call this function, giving it as parameters or as argument the start date and the end date of our period that we are interested in. after that, we'll move to the loop. So we said we have to loop over years, months, and days, as you can see here, for dates that we defined already in this function. You give the value of the year to the attribute year, months, and days, and you can rename your data sets like this, put in the year or add in the year, month, and day to your file, so you can distinguish, or you can explore your files or organize your repository as you like. All right, let's move to the reforecast. The reforecast has been produced every Monday and Tuesday of each week until the release of the new integrated forecasting system, cycle 49R1. So the medium range forecast now is run for fixed days of the month, which are those days. But the reforecast data is not available in EWDS recently, starting from November 2024, but we will put it back in the EWDS as soon as possible. And if you are interested in the reforecast, please raise a ticket or write to us, and we will provide the data for you. So for the reforecast, the best practice is to loop over months, days, and make your area of interest precise if you are interested in a small area, because that will make your download time shorter. So please define your area of interest. Okay, so let's move to the code snippet. The first thing to do is to define a function to get the month days that we are interested in. We are interested in Mondays and Thursdays for every week. And after that, you can loop over the years and the months and execute your or run your request. And as we did before, you can rename or put the date in the file name, so it will be easier to analyze and explore after. All right, let's move to the seasonal. The best practice to download the seasonal GloFAS is to loop over years and month and make your area of interest precise, same as the reforecast. And you can explore, you can run the cell now, or if you have set up your Python environment, or you can try it later. And if you have a problem, please come back to us and write to us, and we will fix the problem for you. Okay, the last part of this notebook is retrieving GloFAS seasonal reforecast, and we will follow the same logic that we followed before for the seasonal and for the reforecast. And the best practice is to loop over years and months and make your area of interest precise. Okay, I hope that it's a bit clear for you. Okay, if we still have time, we will move to the part 3, which is a little bit advanced, but it's a good use case if you want to play or analyze GloFAS data against observational data from your area of interest. Okay, let's start the third part and the last part. This notebook will walk you through how to map the station to the correct GloFAS cell. We said, let's suppose you have an observational ghost station in your area of interest, and you want to check or you want to compare GloFAS simulations against your observational data. So if you want to do so, please follow with me this notebook. We will start by mapping the station to the correct GloFAS cell, download GloFAS climatology of the corresponding cell, visualize observed and analyze discharge data, calculate and assess the hydrological model performance metrics, fit Gamble distribution and calculate the thresholds, visualize the thresholds and the hydrograph of the whole period, and read static data, which are available through the EWDS. You can download the static data, which are the thresholds and the up area and many more. And finally, compare and visualize station-based thresholds against GloFAS thresholds. I suppose you have already had discharge observations from stations in your area. In this notebook, I will use as an example an observational station located in the northern Morocco that is present in both GloFAS and EFAS datasets. And below, you will find the metadata details of this station here. Okay, so the first thing to do to make things clearer is to start a QGIS project, and I suppose you are familiar with QGIS. And yeah, so I don't think we have time now to start a QGIS project and do the mapping, but I will go through these Jupyter notebooks and the Jupyter notebook, and you can try it later on your own. Okay, so when mapping the station using the provider's coordinates, you may notice a slight discrepancy in position compared to GloFAS coordinates. And this difference occurs due to the variation in spatial resolution between datasets. So I have some screenshots from my QGIS project. So as you can see here, I have this point with the provider coordinates and this point with GloFAS coordinates. So they are not the same, and we have to decide which cell from GloFAS we should download to compare to our station. Next, you have to upload or import the up area netcdf file into your QGIS and check if the station point falls within the same grid cell as the corresponding GloFAS coordinates. As you can see here in the screenshots, we have the GloFAS cells, and we can see that almost the 2 points are or falls within the same cell. And the next thing to do is to ensure that the upstream area of the station as provided by the data provider closely match the upstream area of the corresponding GloFAS cell. And I will go back to the metadata of our observational station, and the drainage area is 498 square kilometer. So here we will compare with the up area in GloFAS cells, and we can see clearly that this red cell has a value of up area really close to our provider up area. So to compare our observational time series with GloFAS simulation, we have to download data for this red cell. And to find more details about the mapping station, please see this link here. And please go back to us if you find a problem or if something is not clear. Please write to us in the chat. Okay, so we will start by downloading GloFAS climatology of the corresponding cell that we found before. using the API and using the same logic that we've seen before in the previous notebooks, and you can go back to them to be sure. And after mapping the station to the correct GloFAS cell, we need to extract the coordinates of that cell in order to compare it with our time series. And we assume that you have already completed this step and identified the coordinates of the cell that best represent the station. And if you extract the coordinate of GloFAS cell from QGIS, this is really important, the longitude will be in the range minus 118 to 118, whereas the grip file use longitudes in the range 316. Therefore, you need to add 316 to the longitude values if it's negative to match the grip file convention. Okay, as you can see here, those are the longitude and latitude from QGIS. And we will not use this value because we have to add 316 to the longitude to download data from EWDS. Okay. Let's move on. Now we want to calculate the performance metrics for our observations and compare it to GloFAS. Let's see. Okay, in this cell, we will define and calculate the performance metric functions, and those are the same performance metrics we are using for GloFAS, the KGE, Nash-Sutcliffe, the bias, variability. Okay, now let's move to the next cell, and we will visualize the observed and simulated discharge data to have an idea what are the differences between our observational discharge and the GloFAS discharge. The next following cell, we will visualize the hydrological model performance metrics, as you can see in the graph here. And you will find the same graph in GloFAS if you want to check the performance of the model in every cell you're interested in. Next, we will feed the Gumbel distribution and estimate the return period thresholds and visualize the hydrograph. And this is the result. You will find almost the same graph in GloFAS. If you click on a reporting point, you will see the return periods and the thresholds. Okay, for GloFAS, we also provide the thresholds used. So if you want to compare your calculated thresholds and GloFAS thresholds, you have to run this cell, and I'll show you the result. Here you will get a graph that will compare the observed and GloFAS flood thresholds. I know this is a little bit advanced, and but it's a bit easy, and you can play with data on your own, and that's it for this session. And I hope I was clear and brief. And if you have any comment, feedback, please write to us in the email or in the chat. Thank you.